Okay, I do want to welcome you to this laboratory. This is the VSEPR theory, a molecular geometry laboratory. It's going to be helpful to have on hand, of course, this particular worksheet, but also the little white spheres and the toothpicks that we've been using in class. So if you've got those, follow along with me. Let's start with H2 gas. So hydrogen gas is, of course, composed of two hydrogen atoms. Here they are here. And those two hydrogen atoms are being held together by a pair of electrons. Each hydrogen brings to the Lewis structure a pair of electrons. But what is interesting to note here is that each hydrogen is pulling in the opposite direction. That is, each hydrogen has its own electronegativity, pulling the electrons towards it. I don't know what that electronegativity is, but I do know that whatever the electronegativity of this hydrogen is identical to the electronegativity of this hydrogen. And so the two hydrogens are pulling in exactly the opposite direction. The 3D drawing that we'll use is this one right here. We'll use two little circles to denote the two hydrogen atoms, and of course the electronegativity bars going to the left and to the right like this, but in exactly the opposite direction. So that tells us that the bond polarity is nonpolar. Remember that nonpolar means symmetrical. Nonpolar means symmetrical. So the bond polarity, because there's only one bond, is going to dictate the molecular polarity as well. So in this case, we've got only one bond between the hydrogen and the hydrogen, and so that bond polarity, because it's symmetrical, is going to make the molecule as a whole nonpolar as well. So we'll write nonpolar in this box right here. Now let's talk a little bit about the molecular geometry. Well, it's pretty clear that the two atoms are connected by a line in this case. We can think of the bond between the two atoms as a line, and the shortest distance between two atoms or 2 points is a straight line. So we call this linear. So the first structure, H2, we would call linear. That's the molecular geometry of this shape. So let's move on to a structure that's a little bit more complicated, but not very much at all, and that's chlorine gas, or Cl2. Now, chlorine gas is going to be composed of two atoms of chlorine, obviously, and those two atoms of chlorine are going to be connected by a pair of electrons. And so the pair of electrons is shown between the two chlorine atoms. But notice also that this chlorine and this chlorine, whatever the electronegativity may be, whatever it is, it's the same on this side as it is on this side. And so we draw the electronegativity arrows just like that. So this way for the chlorine here and this way for the chlorine here. We'll draw the 3D structure as two larger spheres like this and like this with the electronegativity arrows pointing in the opposite direction. I don't know what the electronegativity of chlorine is, but I do know whatever it is on this side, it's identical on this side. And so that's going to cause me to determine that the bond polarity between the two chlorine atoms would be nonpolar. Nonpolar for the bond polarity, and since there's only one bond between the two atoms, that's going to dictate the molecular polarity. The molecular polarity would be nonpolar. In other words, what we're saying here is that there is no difference on either side of this molecule. That the left side and the right side are identical. And so we call the bond nonpolar, but we call the molecule nonpolar as well. What about the molecular geometry? Same as above. The closest distance between 2 points is a straight line. So this would be a linear structure, Let's move on to the next one. This time we have hydrochloric acid, or HCl. Now it's important to note that hydrochloric acid, while it's composed of two different atoms, a hydrogen and a chlorine atom, is still linear because, again, the closest distance between 2 points is a straight line. But unlike the previous two structures, remember that chlorine is a higher electronegativity than is hydrogen, so we point the arrow towards the chlorine, and there's no opposing arrow. There's not another one going towards the hydrogen. So we'll draw the structure like this. We'll draw the chlorine a little bit bigger than the hydrogen. It is a bit bigger radius, so we'll draw it a little bit bigger. But again, the shortest distance between 2 points, a straight line. This would be a linear structure. Now, let's talk about the bond polarity. Unlike the previous two structures, this time chlorine is more electronegative than hydrogen. There's no opposing electronegativity. This is not balanced, so the bond polarity would be polar. And because there's only one bond, the molecular polarity would be polar as well. In other words, there's two different sides to this molecule. There's what we call a more electronegative side and a more electropositive side on this end. So it would be a linear molecule because of that characteristic. There's only one bond, so it has to be linear. Now let's go on to water, H2O. Water has a peculiar shape because of the fact that it has a lone pair of electrons. Let's take a look at this lone pair here and this lone pair here. Actually, it has two lone pairs of electrons. Oxygen has the lone pair, and the oxygen is what has the higher electronegativity of this bond and of this bond. So we'll draw the electronegativity arrows in that direction. If we want to draw this in 3 dimensions, it's good enough just to put an oxygen here, a circle here for this oxygen, a hydrogen here, and that'll be fine. Make sure to point the electronegativity arrows towards the oxygen, the more electronegative atom. Note again the lone pairs of electrons here and here. That's going to dictate this structure. It's not going to be linear this time because of the fact that those electrons are going to push this hydrogen and this hydrogen towards one another. It's going to push them down, making this a bent molecule, not a linear molecule. So now let's look at the bond polarity. Hydrogen and oxygen are not the same atom. So therefore the bond polarity would be, well, it's a polar bond. They're not the same molecule, the same atom. Oxygen more electronegative than is hydrogen. This is a polar bond, as is this one. Hydrogen less electronegative than is oxygen, polar bond. So both bonds are polar, so we'll put polar right here. But the molecule as a whole is also polar because it is not a symmetrical molecule. On this side of the molecule, we have an electronegative end. On this side of the molecule, an electropositive end, right? And so therefore, we're going to say that the bond is polar, each of the bonds are polar, but the molecule as a whole is polar as well. Let's go to the next structure. Here we have carbon dioxide. Carbon dioxide contains 2 double bonds. So in the Lewis structure, we'll see a double bond on the left and a double bond on the right. These electrons here, 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 and here really do not affect the geometry of the structure itself. It's only the central atom that matters. In this case, we have an electronegativity arrow going to the right and one going to the left of equal magnitude. And that makes the structure linear. There is no lone pair, as there was in the previous example for water, for 2 lone pairs of electrons pushing these hydrogen atoms, making them bent here. There's no such lone pair on the central atom here. And so this and this, according to VSEPR theory, are going to move out as far away from each other as possible. This is a linear structure. How about the bond polarity? Well, carbon and oxygen, clearly not the same atom, so it's a polar bond, but notice that the 2 arrows are exactly opposite to one another. It's a non-polar molecule. Overall, this arrow and this arrow cancel. It's a non-polar molecule for CO2. Exactly balances each other out. Let's look at boron trifluoride. Bf3 boron is an exception to the octet rule. Ordinarily, we would see 8 electrons. This time, we're going to see 6. 2, 4, 6 electrons surrounding the boron. Fluorine is surrounding the boron. There's 3 of them, and we're showing the electrons here, here, and here. But notice on the 3D model, we're doing the best that we can, or I'm doing the best that I can to show 3 dimensions. I'm using this wedge to denote the fluorine here coming out at me, this dotted line, the fluorine behind me, and then this fluorine in the plane itself. So the important thing is that all 3 of these atoms, all 3 of the fluorine atoms are in the same plane. Use the little white spheres and the toothpicks to convince yourself of that. This arrow, and this arrow completely cancel each other out. And so even though the bonds are polar, boron and fluorine are not the same atom, boron and fluorine not the same atom, boron and fluorine not the same atom, the bonds are polar, the entire molecule non-polar. It balances each other out. All the 3 arrows are going to balance each other out. Use the little model, the styrofoam balls, to try to convince yourself that that is the case. We call this structure trigonal planar. Trigonal because there's 1, 2, 3 fluorines surrounding the central boron. Planar because everything's in the same plane. Let's look at the next structure. We have ammonia, NH3. Nitrogen in the center with 1, 2, 3 hydrogens surrounding it, but note a lone pair of electrons right here. That lone pair of electrons is going to be important in the geometry because it's going to force this hydrogen, and this hydrogen down and away from the electrons. Okay, notice the direction of the arrows towards the hydrogen in this case. But the point is this, the point is that this is no longer going to be considered a trigonal planar structure. Now it's trigonal pyramidal. The lone pair of electrons in driving these hydrogens down are going to cause a pyramid shape. Now, polarity. Nitrogen and hydrogen, not the same atom, so the bonds are polar. But what about the entire molecule? Unlike the previous molecule, Bf3, where everything is in the same plane, in this molecule, NH3, everything is not in the same plane because the lone pair of electrons forces these three hydrogens down, and so the bonds are polar, but the molecule is polar as well. Let's go now to CH4. CH4 has a carbon in the center and 1, 2, 3, 4 atoms around it. Notice I'm using these little lines, these little dashed lines right here to denote those electron pairs. Here in the three-dimensional structure, a little bit difficult to draw, but I'm using these wedges to denote hydrogen coming out at me, hydrogen coming this way, hydrogen that way, and then one hydrogen up. All four of these arrows are going to cancel each other out. Once again, use those styrofoam spheres to convince yourself of that. Let's take a look at the bonds. Each of the bonds is polar. Carbon and hydrogen is not the same atom. Carbon and hydrogen, of course, not the same atom, and so on. But the entire molecule would be nonpolar because everything cancels each other out. There's one up, three down, but they cancel each other out. It's hard to see on a two-dimensional page, but it's easier to see with those styrofoam balls. So tetrahedral would be the structure for this CH4 structure because we have one thing in the middle. Tetra means four. 1, 2, 3, 4 things surrounding it. Let's look at the PCl5. Here we have phosphorus pentachloride. Phosphorus in the center, and we have 1, 2, 3, 4, 5 chlorines surrounding the phosphorus. Now let's look at the 3D structure. Phosphorus here, we've got a chlorine, a chlorine, and chlorine. Try to denote that all in the same plane. Chlorine up, chlorine down. Everything is balancing. So even though we look at a particular bond, say phosphorus to chlorine, which would be polar because they're not the same atom, the entire molecule we're going to call nonpolar. It is absolutely symmetrical. The entire structure, three in the plane, one up, one down, is called trigonal bipyramidal. A pyramid on top, a pyramid on bottom. Use the little white spheres to convince yourself that this is a nonpolar molecule. And finally, sulfur hexafluoride, a very dense gas. Here we go. Here's the Lewis structure for sulfur hexafluoride. We've got sulfur in the middle, fluorine, 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 fluorine. That's four of them, one down, one up. Notice I've drawn in the Lewis structure all of the electrons, but it's not so important in a three-dimensional structure. I'm trying to denote this fluorine, this fluorine, this fluorine, and this fluorine in the plane. One fluorine up, one fluorine down. That's a lot of arrows. Each one of them is polar, right? Each one is polar, but the entire structure, again, you're really going to need those white spheres to convince yourself of this, and make sure that you accurately put those little white spheres together to show yourself that the entire thing balances out. So the whole thing, the entire SF6 molecule is nonpolar. And when we have four things in the periphery, in the plane, one thing up and one thing down, we call that octahedral. Octahedral because we now have two structures, one on top, one on bottom. Each one of them has four faces. Four faces. You're going to need the white spheres to show yourself that that's the case. So use those and create this molecule. It is called octahedral. That's it for now, folks. I'll see you on the next one. Thank you. Bye-bye.